Welcome to Chapter 10 of Astronomy. This chapter is going to be the final chapter in our second unit about understanding the solar system. Now, this chapter is going to be and this video, likewise, is going to be relatively brief because we only have one object left to talk about in the solar system. Interestingly enough, we have saved what is no doubt the most significant and by far the largest for last. And the last thing that we have left to talk about in the solar system is, of course, the sun itself. This chapter is entitled, The Sun, Our Extraordinary, Ordinary Star. Now, I'm going to explain that very briefly. What that means is our sun is remarkable. There's no doubt it is an extraordinary, fascinating device. It is a powerful machine. It is a complex system. And there is science going on the sun that we cannot duplicate on the Earth. But yet, this amazing, extraordinary device, in the grand scheme of the cosmos, is just a very common, regular star. And our sun, as amazing as it may be, shown here by looking at the ultraviolet light coming off of it, is just a fantastically amazing device. But yet, it is one of many stars just like it. Now, like everything else in this section, we have a vital stats page on 318. Looking here, we see things about its size, roughly how big it is. That it is almost, it's 300,000 times more massive than the Earth. And it is... its diameter is something on the order of 1 billion times more, it is an enormous size. However, this remarkable device has some important statistics that we need to look at. One of the things I want to point out here is travel time to the Earth. And what this is an interesting concept to explain. If we wanted to know how long does it take light to get from the Earth to the Sun, the answer is about a little over 8 minutes. Around 400 seconds or so. It's about how long it takes light to get here. And that's due to the distance that it is away. Remember back in Chapter 6 when we talked about the distance the Earth is from the Sun, which is what we call an astronomical unit. That one astronomical unit takes about 8 minutes, a little over 8 minutes to get across that distance. The other thing that I want to point out here is the temperature. The temperature of the surface, and we're going to talk about what the word for that surface is here in just a second, is about 5,800 Kelvin. That temperature puts it right in the middle of the visible part of the spectrum so that we can see the light coming off of this thing. This is in the visible part. There are other areas, there are little pockets on the sun, like in this picture just on the previous page, where there are hotter areas that are emitting light. These little blobs are little light being emitted in the ultraviolet, because the sun does not emit just visible light in this 5,800 range, but it also emits ultraviolet as well as even into the X-ray range in certain areas. Now, the first thing we need to start off with is what we're going to call the sun's atmosphere. And really, when we're looking at the sun, really what we're seeing is just there's an outer layer that we can see, and we simply can't see down inside of the sun very well. And so the layer that we have to work with is called photosphere. And of course, if you break those two words apart, sphere is like a spherical object, and photo translates into light. So this is, the ball of light is what that's saying. And that is the description of the part that we can actually see. Now, the photosphere, we see, one of the things they talk about over here is this concept of limb darkening. That as you look onto the edge, you're looking into more and more of the atmosphere, and it makes it look darker. Whereas in the center, you're looking in more directly. This same effect actually happens in reverse on the Earth, where when you're looking on the edge through our atmosphere, it causes an effect of, we see a change in the color of the atmosphere of our own planet, right? We see blue skies in the middle, and we see reddish colors on the edge for our own planet. Similar effect is happening with the moon there. Excuse me, not with the moon, the sun. Now, going on down a little bit deeper, looking in a little more detail, one of the things we see is this idea we call granulation. The surface of the sun looks grainy, looks like sandy, if you will, where it's not a smooth surface. We see all these little cells all over the photosphere. And what these are is they are channels, so to speak, of where we see the hotter gas coming up from the inside of the sun and the cooler material floating down. Now, remember, we talked a little bit about this earlier, the idea of how a star works. We talked about this in Chapter 5 about, the stars are making heavier elements, and there is a balance that has to exist. The balance comes between the gravity that is pulling this thing down, gravity being the attractive force pulling the star together, the gravity versus the pressure. Because inside the sun, it's very, very hot. The surface may be 5,800 Kelvin, but the inside of the sun may be 10 million Kelvin. Extremely high temperatures. And so those high temperatures produce high pressure, and that's what's pushing back out. So there is this balance between pushing out from the high temperature and pulling down in from the gravity, and that gets into a state of equilibrium that holds the sun in roughly the same shape. Now, that movement of the material in and out, though, is seen in this effect of granulation, which is a neat concept showing us the balance of this thing happening. Now, the outer layer, the outermost layer that we can see is called the chromosphere. And the chromosphere is a very thin, very, very low density gas that can actually become extremely hot, but it's very, very low density. So we'll see, this is where we see sort of the feathering on the edges here, shown here in the chromosphere. And then over on in section 10.3, it talks about the temperature increase higher in the sun's atmosphere, which is a fascinating concept. And when you're going through doing your reading here, you'll see some information about how that temperature change can occur as you get further away from the sun, which is a remarkable concept. And they show this, you can see this visually over here on 322 during a solar eclipse. This is where the moon is blocking out the sun, and we see this effect of the solar corona out here. And at this point, the temperature of this corona, if you see over here, may spike very quickly all the way up to as high as 1,000,000 Kelvin, 1,000,000 degrees out here with this very, very hot gas that's getting away from the sun. So the atmosphere of the sun is a complex, exciting part that we get to look at. That's the stuff that we can actually see relatively easily. Now, the big part we need to look at with the sun is the fact that the sun is active and it's changing. And in fact, this concept is most easily seen by of what we call sunspots. Sunspots are actually a darkened area on the surface, and sunspots have been known about for centuries. In fact, Galileo observed sunspots with his telescope. Now, you would never want to do this without a proper filter, but you can take a telescope and look at the sun and see these dark spots. Now, without a filter, you will go blind if you try that. So if you own a telescope or binoculars, don't go out and look at the sun to look at sunspots without a proper filter. And I hope in this class that we'll get to actually try to do this. I have some filters that we can use to actually see the surface of the sun safely. And when you do so, you can see some amazing detail in these. But the thing that's interesting, sunspots have shown us over the years that, first off, it is proof that the sun is rotating. We can see them move. So day after day after day, these sunspots march across the surface, indicating that the sun is spinning, which is a very useful part to look at. The other thing that we have seen from sunspots is that they have a well-defined cycle of when they show up and when they go away. This is called part of the solar cycle. That's part of an area of activity or an inactivity. And what we now have determined is that these sunspots appear to be driven by magnetic fields. That is, the sun also has some of this magnetic properties like we saw with the Earth and Mercury and Jupiter, for example, that have those having significant magnetic fields. The sun obviously has a strong magnetic field, and that appears to be creating a big part of what's going on with the active sun. And we notice that it's active when we see a lot more of those sunspots. So there's clearly a relationship going on between those two. The magnetic field also creates other phenomenon. Prominences, for example, are shown for you on 330. Some beautiful shots there of these arching spirals of material coming off of them, creating this effect. But perhaps the one that is by far of the most interest to us as humans is this thing down here shown on 331 called a coronal mass ejection, or CME. CME is very exciting because this is effectively a huge explosion of energy off of the sun. It's this great burst of energy coming out. And this can actually have a significant effect on the Earth, and in terms of being potentially something that can be harmful to us. This burst of energy could do some damage. But what shields us is, of course, if you look right here, you see we are protected by that all-powerful magnetic field. That dynamo effect going on inside of our planet shields us. Now, what this does cause, very often when we have a CME, is this energy will be warped around and come down into our planet, into our atmosphere, and cause the aurora borealis, or the aurora australis, that is the northern lights and the southern lights, where we see the lights glowing because of that effect. It's a very neat part going on when our sun is active. Now, I gave a little teaser of this before about this idea of thermonuclear reactions producing the sun's energy. And what that means is there is nuclear fusion going on inside of the sun. The sun is taking hydrogen atoms, smashing them together, and forming heavier elements, and in doing so, releases energy. Now, this is a very exciting thing, and when you read through 10.7, this is really a key concept of understanding the function of the sun. So make sure you read through that well. But this is really neat to see where we use one is almost undoubtedly one of the most well-known mathematical formulas that comes from science is Einstein's very famous E equals mc squared. Well, what this means is the energy that is being released equals the mass that is being converted, and then that c is a constant, the speed of light. So what they're saying here is there is a direct relationship between the energy and the mass that is being lost in these nuclear reactions. And so what happens is the sun is actually using up its mass, and in doing so to release this energy. And so there's this comic over here, and I would highly recommend you read through this Astronomer's Toolbox on 333. It explains this process and how the energy is being lost. And each one of these reactions produces a tiny change in mass. But that tiny change in mass happens a whole lot of times every second on the sun. And this comic is great. He says, after reading that the sun loses 600 million tons every second, is it still there? Well, it's still there. Well, how does it look? It looks pretty much the same. Well, if the sun is losing, 600 million tons every second, why doesn't it look different? Well, the answer is 600 million tons is nothing to the sun. That's a tiny amount. That's literally a drop in the bucket, a drop in the ocean, if you will, compared to the mass that the sun has. The sun has, 2 times 10 to the 30th kilograms of mass. So a couple hundred tons is nothing. It's an irrelevant amount of mass for it to lose every second. So what that means, though, is that there is effectively a time limit on how long the sun can do this. And the good news is, you could think of it kind of like saying, like it's a gas tank, right? So if you have so much fuel in a tank, you can drive for so long or so many miles before you're out of fuel. The sun is doing a similar thing. It has a certain amount of fuel, and it's consuming it. And it's doing so at a set rate. And so if we know how much fuel it has, we know how fast it's using it, we can project how long we think it will be there. The good news is, it's probably got about 5 billion years worth of fuel left in it before it goes through any significant change. So, you and I are perfectly fine. The sun is not going to be changing anytime soon, unless something drastic changes about the way we know the sun works. So they give a couple of great explanations for this. 333 and 334 give some excellent diagrams explaining how this works. If you flip over to 336, I did want to mention this one too as well. Answering, what is the sun made out of? There is a list showing you that about a little over 90% of the total atoms, or about 70% of the mass, is made out of hydrogen, and about 8% out of helium. So that means 99.9% of the sun is made out of nothing but hydrogen and helium. What that means is this hydrogen is ultimately the fuel. So the sun has got a whole lot of fuel left. Almost all of its mass, almost 70% of its mass is tied up in hydrogen. So it's got plenty in the tank to keep going for a long time. The sun will be burning long after I am gone, I would imagine. The last thing that they talk about in chapter 337 is a cool research area. It's talking about this idea of a neutrino. And neutrinos are a complicated idea, and I encourage you to read through this. It's an idea talking about this particle coming from the sun and how it has an effect to be able to go through things very, very well. And there's a really neat diagram about the solar neutrino experiment and how we're trying to understand this mysterious particle, this neutrino, to try to get a better sense of how it works. It's a fascinating read there right at the end of the chapter. So make sure you're going through the reading on the chapter. Check out the PowerPoint, and that should get you ready to go for the assignment on chapter 10, which will be the last part of this unit, so we'll be ready for our unit exam number 2 very shortly. Good luck.